So in this video, we're going to introduce the derivative as instantaneous rate of change. Now, in the video on the motivation for limits, which you should watch before this video, we motivated the idea of limit by thinking about the concept of velocity at an instant, or instantaneous velocity. So this concept of velocity at an instant, or instantaneous velocity, motivates the concept of limit that we've been thinking about for the last couple weeks. And now in this video, the derivative, which is one of the central concepts in calculus, is itself a generalization of the idea of velocity at an instant, or instantaneous velocity. And so in this case, where we're talking about velocity, we're talking about a position as a function of time. If we take that position as a function of time and we generalize that to any function, right? So in this case, we have position as a function of time, but if we replace that with any function, right, f as a function of x, the derivative is the analogous concept to instantaneous velocity. So this derivative of this function f of x is the instantaneous rate of change of the function at a particular point, whereas the velocity is the instantaneous rate of change of position at a particular time. Okay, so that's what we're going to discuss in this video. So to begin, let's roughly recall that the instantaneous velocity, so at a particular time, it's the limit of average velocity over shorter and shorter time intervals. Okay, so let's make this precise now. So to be more precise, let's say we have x of t is position x at time t, right? So we have position as a function of time. We're measuring our position along some one-dimensional line as a function of time. So we want to translate this idea of that instantaneous velocity is the limit of average velocity over shorter and shorter time intervals. So that's what this expression is here, and let's break it down to see what it means. So the whole complicated looking thing right here, all this is writing down is the average velocity over a particular time interval. Okay, so the time interval is from t0, so this is some particular time, right? We're interested in the average, or in the instantaneous velocity at the instant t0. And so we look at a short time interval. So we start at t0, we let a little bit of time delta t go by. Okay, so we're looking in this time interval. And what is average velocity in that time interval? Well, velocity is a measure of change in position over change in time. Okay, so your average velocity is change in position over change in time. And we can abbreviate that delta x. So the delta is just a generic symbol for change. So change in x over change in time. And the change in time, that is just this short time delta t. Okay, so delta t you can think of as just some small number, some small interval of seconds. And what's the change in position? The change in position is just this numerator. Right? It looks complicated, but all it's saying is you look at x at, so let's start here. So you look at x at the initial time, right? And then you compare that to x at the initial time plus the amount of time you've allowed to elapse, right? So this is just an expression for the ending time. Right? So you start at t0 and you allow a little bit of time to elapse, and then you look at your position at that time. Right? And once you have your position at your stop time, you compare that to the position at the starting time by taking the difference. Okay, so that's breaking down this whole numerator. All it's saying is the change in position. Okay, you're comparing position at the stop time versus position at the starting time. So you have change in position over change in time. That is your average velocity in the time interval. And then our instantaneous velocity, according to our rough idea, that should correspond to the limit of these average velocities as your time interval gets shorter and shorter. So our time interval getting shorter and shorter means this delta t, the amount of time we allow to elapse, should go to 0. Okay, so you're just taking, this is your average velocity over your little time interval, and this is you letting the little time interval get shorter and shorter and shorter. And that limit, that is going to be the instantaneous velocity at t0. Okay, so one more time. this expression here, this is change in x, right? X at the ending time, or you have a little bit of interval of time, right? You start at some time, you let a little bit of time go by, you look at the position at the ending time, you compare that to the position at the starting time, that's your change in position, your delta x, you divide that by delta t, right? Because your velocity, your average velocity is comparing that change in position to the change in time. So that's your average velocity over the time interval. And then you allow the time interval to get smaller and smaller by allowing this elapsed amount of time, delta t, to go to 0. And that is the instantaneous velocity. By definition, this is how we define the instantaneous velocity of our position function at t0. And so we have some notation for this concept. The instantaneous velocity at t0, which is this limit here, the limit of the average velocities, that's denoted one of two ways commonly. This is read as x prime of t0, this first one. I've indicated that here. Okay, so you have x prime at t0, x prime at t0, or the derivative of x with respect to t. That's how you read this thing. Sometimes it's said dx by dt, the derivative of x with respect to t at t0. And generally either one of these things are called the derivative of x, okay, at t0. And it's just the concept of the instantaneous velocity at t0. So the instantaneous velocity at t0 is equivalent to saying the derivative of x at t0. Okay, so the derivative of x of t at t0, that's equivalent to the concept of instantaneous velocity at t0, and it's denoted one of two ways, as x prime or this dx by dt notation. So as I said in the intro, our next move is to generalize. And the reason for this generalization is to simply ask yourself, why would we restrict ourselves to only talk about position, time, and velocity? Right? So position, time, velocity, we're asking how position changes as a function of time. But the whole natural world is in a state of flux, right? Various variables depend on other variables or changing as other variables change, right? You change inputs and outputs change. So for example, pressure, things like pressure, temperature, electric charge density, etc., are functions of position in space. And economic demand, for a particular product might be a function of price. Animal populations change with time, and so on. Right? So we have these various variable quantities that are functions of other independent variable quantities, and we want to be able to describe the rate of change of such quantities. So here's how we generalize the situation. In the left-hand column here, we have the situation for instantaneous velocity. On the right hand, we're going to have derivative in general. So when we have instantaneous velocity, our independent variable is t for time, and our dependent variable is position, x. So x is a function of t. In general, we just use x to be our independent variable. Okay, so over here, x denotes position as the dependent variable. In general, usually our input variable, which is the independent one, is x. So don't confuse this x in this situation with velocity and position with this x over here. So in general, we usually just use x as our independent variable. And the dependent variable is f, which is just our general function. Okay, and we're interested in this case, in the velocity case, instantaneous velocity at a particular time. And in the derivative, we'll be interested in the derivative at x0 at a particular fixed point. Now, in the velocity case, we find the instantaneous velocity by looking at the average velocity over a small time interval. Okay, so we have a small time interval, as we discussed before. And we look at the average velocity over that interval. So the change in x, the delta x, over the change in time. In the derivative situation, we consider a small x interval, right? An interval of small x. So a small interval of x values, so x0 to x0 plus some small delta x. And then we consider the average rate of change of f of x over the interval. And what that means is we look at how f changed, right, the delta f, relative to how much x changed. And same as over here, how much the position changed over here relative to how much the time changed. That now just becomes how much the output value of the function f changed relative to the change in the input value. And you can see the formulation is exactly parallel here. We just changed the names of the independent and the dependent variables accordingly. Okay, so this is how our function changed over the interval. We looked at the function at the right endpoint and compare it to the function at the left endpoint, and then we compare them by subtracting and divide by the change in x. That's our average rate of change of f over this interval, the same way our average velocity over this small interval was given by the same analogous expression. And then the final step was to obtain the instantaneous velocity at a particular time. We let the size of the time interval go to 0, right, by allowing the time that elapsed to create the time interval to go to 0. And that was our derivative, x prime at that particular time, t naught. While in the case of our general function f, right, this is what we're trying to capture is the instantaneous rate of change, right? So we have the average rate of change of f over a particular interval. We capture the instantaneous rate of change of f at this point x naught by, again, just taking the limit as this interval up here becomes small, right? So you let delta x go to 0, so this interval is shrinking to a point, and all along you're looking at the average rate of change, and you're allowing that interval to go to 0, and that should intuitively capture the instantaneous rate of change of the function at that point. So to wrap this up, I just want to make sure it's relatively clear what f prime of x naught means, what the derivative of f at x naught means. Okay, it's the instantaneous rate of change of f of x at x equals x naught. This is analogous to the instantaneous velocity at a particular time. So velocity is rate of change. So we're just sort of swapping out rate of change for velocity. The instantaneous rate of change of our function at x equals x naught. And what does this phrase instantaneous rate of change mean? What it means really is that what we're measuring is how our function f of x changes relative to a vanishingly small change in x away from x naught. Okay, so we're measuring how if we change our x at x naught just by a little bit, right? So that's this plus delta x. We change that a little bit, we see how much our function changes, and we're not just interested purely in how the function changes, we're interested in how it changes relative to this vanishingly small change in x, right? And the vanishingly small, that's the limit here. Okay, so our f prime of x naught, way you can think about it, I mean, it's precisely this limit of delta f over delta x, but it's going to be approximately the change in f over the change in x when delta x is very small. And the approximately is because of the limit, right? So we get the exact quantity in the limit when delta x totally vanishes, goes to 0. But when delta x is very, very small, we get an approximation. So approximately speaking, f prime at x naught, it's the change in f relative to the change in x, as long as that change in x is very small. Okay, so the derivative at x naught is how our function changes relative to a very tiny change in x. So we change x by a little bit at x naught, and we see how much our function changes, and then we see the relative change there, right? So we compare how our output changed to how our input changed. And that, when that input is very small and in the limit goes to 0, that's our f prime at x naught. Okay, instantaneous rate of change of our function at x naught.